Hey.
Hello.
Hello. Where's Holly?
I don't know. Should someone call her? Or is she coming? No, I should not here. I can still have continue. Oh, she's here. Great. So we have everyone this time, right?
Okay, I think we are both here, so maybe we can start.
Okay. Does anybody remember where did I stop last time? Okay, so how about like that? I'll start going over some definitions because you probably forgot them. And then when you come to the one I didn't tell yet, like last time, you just tell me and I stop and I'll become more detailed. Does it work? Hey? Sure, thank you, Theodora. Okay, so we were talking about metric topology, which is like super important for a lot of different reasons, especially because, you know, where people would like to quantify everything. And so we defined that a metric D from X to X into R should have, it's like a function which should have the following property. And X is our set on which we base a topology. And so first is dxy. It's bigger or equal than 0 for all xy in the x. And the equality holds. So basically this is equal to 0. Like if and only if we have that x is equals to 0, x is equal to y, right? And that makes sense because we want distance to be a real, like something positive, or at least non-negative. And then second, we want it to be without orientation. So you want it to be like this, right, for all y and x. And then, yeah, you can always stop me if you want to see something because I know I erase everything very quickly. So dxy plus dyz bigger or equal than dxz, which is called triangle inequality. Okay, and so these are the main properties we have to remember about the metric, and that's basically all. Everything else is just something that comes with a specific metrics we know. And we also have a thing called epsilon ball centered at x, which is this. Dx epsilon equals to y is that dxy is less than epsilon. So basically, it's just a set of all points which are contained in the ball, and its radius is epsilon, right? And inside points of the ball are also counted. Okay, and then we basically were talking about the metric topology induced by D. And what did we say is basically that those balls with radius epsilon are like the basis of that topology. So yeah, and we showed for different reasons what does it hold, and I will not talk more about that because that's kind of long, and I went over it last time. I think, okay, and then a specific thing we want to be true is if X is a topological space, we say that X is metrizable. If there exists a metric D, if there exists a metric D on a set X that induces a topology of X. Induces the topology of X. Okay, so basically, as we understand from the definition, not everything is metrizable, but a couple of nice things are. Okay, and so what do we have later is we also have a definition of a diameter. So diameter of some set is a supremum d a1, a2, a1, a2 in the A. So it's basically like the largest distance that's possible between any 2 points in the set A, right? And so if the diameter exists, it means that the set is actually kind of bounded, right? Because it would have some maximum. Okay, and so what do we also have is, oh yeah, we have a thing which we want to be true, because we understand that the metric we are putting on a set may not always give a real numbers, right? Because sometimes maybe points are like infinitely distant from each other, right? And so we want a metric which would be kind of similar to the other metric we're having, but it would always give us good results. And so we would call it d bar, right? So for example, let X be a metric space with metric D. And so we define d bar as a function from 2 x's into R by the equation d bar xy is equals to minimum between d xy and 1. So basically, if the distance between 2 points is less than 1, we just take it what it is. And if it's bigger than 1, we just make it 1, right? So basically, whenever 2 points were like infinitely far away from each other, hoops, we make it 1. And of course, it has a lot of like nicer properties, but it also kind of saves some of the things we wanted. And we of course take one randomly, like it can be 5 if you want it to be 5. So it doesn't have to be 1, but we just want it to be something bounded to work with. Okay, and so what happens is that now we want to prove that it's also a metric, but we did it last time. If you don't remember how to prove that, you can go to a video on our YouTube channel before. Oh, by the way, hey Josh is our 2024 student, so he's an incoming freshman. I think he would join our topology seminars if you find himself fit.
Welcome. No, I mean, welcome. Welcome, Josh.
And if you have any questions, feel free to stop me at any point. Like, it's totally fine. Okay, so basically what we're going to talk about now is norm. Norm is also something that you already know or saw before. Say if we have variable x.
Wait a moment.
Which is a vector.
Hey, Aya. Yeah, just a quick question. So you define the d bar, right, instead of d. So what would be the ball on d bar this metric instead of d? For instance, in R. What does the ball looks like?
Give me a second. So basically, knowing our definition it would be y such that d bar xy is less than epsilon. Listen, okay, I guess that would depend a lot on our epsilon. So usually we take epsilon quite small, and so if x and y were like far enough from each other, then their distance would be just 1. And of course, 1 is bigger than epsilon, which we found, so they would never be in the ball. So I think most of the time it stays the same as it was. If epsilon is less than 1, BD bar is equals to BD. And then if epsilon is bigger than 1, then then everything is in the ball. Yeah.
So it seems that this kind of will debar. For D, the topology generated by the matrix D is some ball, right? It's a lot of ball. The subbasis is a lot of balls, right? And now then if you want to find the topology generated by D bar, that means you just trying to find those small balls, right? With radius less than 1, and use them as subbasis, right? This is the only difference in the sense of subbasis.
Okay.
And you will find later they are almost the same in some sense.
Okay. Did everybody got that? Should I repeat that again? Okay, so just to summarize, we have D, which is a metric, which just measures distance between some weird points in any weird set. Sometimes D gives us values of infinity because 2 points are too far from each other. We want it to give us real numbers, so we define D to be something which is always less than 1. And then what we came to is that it's also a metric, and it's just a limited metric. And then the professor asked if we define D4 as a ball. So basically, if we have a point X and we take all points inside of it that are at the distance of epsilon, that would be our ball. And so before, it was just defined on our metric D. How would balls in our metric D bar look like? And we just saw that if epsilon is less than 1, that everything is just the same completely. If epsilon is bigger than 1, then everything is in the ball. So that's what we've done so far. Okay, and then we're gonna come to talk about norms. So you already saw norms before, right? Because basically, say you have a vector, which is x1, x2, blah, blah, xn, right? In Rn. And so we define a norm of it like this, and you totally saw that before. Okay, that's how we define a norm of it. And basically what happens is we define the Euclidean metric D. And Euclidean metric D, on Rn, just to be a norm of like difference of 2 points. So say if you have D, xy, we don't forget that xy in here are not like points on 2D plane. They're vectors. They can be like in any dimensional plane. And then we just do a norm x minus y. And don't forget, this is a norm because first, it's always bigger than 0 or equal to 0, and equals to 0 only when x and y are equal to each other. Second, the norm of x minus y and norm of y minus x are equal to each other. So we know that norm doesn't have any direction, right? So the distance doesn't have to have any direction. And then third, we also know that triangle inequality holds, and I would show that later maybe. Okay, so in here we define we define it to be like this, right? X1 minus y1 square plus blah, 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 blah. So that's basically when we have like, say, 2 points and like, say, 3D, and like we always take like, say, for example, the hypotenuse to be there's like squares, and then you take a square root of it in 2D plane, and you do the same in like 3D and stuff, right? So you all know that. That's what we do every day in our geometry classes and stuff. But then this is only for like when we talk about Euclidean geometry, right? But there are all kind of other metrics. For example, we have square metrics. Square metric, which is a cool metric. I like it. Let's call it P so we don't confuse it with Euclidean. P xy would be maximum x1 minus y1 xn minus yn. Okay, so basically here, instead of just taking like square roots and squares and sum of squares, what we do is we just find what's like the maximum difference in any of the dimensions, and we take it. And actually, I would ask you to try to like draw it, say, for maybe like 2D, and just see how it looks like. Maybe I'll give you a minute to think how it would look like, and then we'll talk about it. And you'll see why it's called square. Also, by the way, yeah, you, I think, have an option of drawing on my screen, so you can just draw here, like this space is yours. And please say something. Okay, to actually give you a better hint, how about that? Instead, I would ask you to find me what would be, what would like a circle with radius 1 look like in that metric. So say if you have some point x and you want to find all points y which lie exactly on with distance 1 from the point x, like how would it look like for us in like 2D, for example? You can unmute yourself, guys. We only have 5 people. Well,
come on. I think you guys should be, in some sense, well, what if I'm not here? If I'm not here, will it be better? Or, I mean, I thought you guys should be quite in some sense, be friends, right? And you should play together a lot of times and eat together a lot of times. So I don't know why you guys are all very hesitated to ask any questions. Yeah, well, you should try to get involved, right?
So let's think together. How about Theodora? Would you be willing to help me?
So we're trying to construct a circle using what exactly?
Using this definition of distance. So we're not using the Euclidean definition of distance. we're trying to think how would a circle look using this metric. And this metric says, okay, so forget about n. This would just be x2 minus y2. That's all. So you're always choosing the maximum distance on x coordinate and y coordinate, and then you're just taking maximum as a distance. And we want to find a circle with diameter 1, so x, y, 1. So all kind of points of y which have radius 1. Well, let me draw it like this. It would have x1, 2, and x2 here. Is that better? Okay, let me give like even more. So like if you have y, and this is y1, and this is y2, we look at this difference and at this difference, and because this is bigger, we say the distance between this point and this point is equals to this, and we just completely forget about this part. That's how we measure distance in this metric. So Zikan is showing thumbs up. Do you have any ideas, Zikan?
We should draw circle first. I mean, in the 2D place, maybe you show us a very good example here.
Yeah, so I showed you how to measure distance on 2D. Can you try to draw a circle on a 2D?
Circle?
Because in Euclidean metric, circle just looks like this because of how we defined distance, right? But if we define distance differently, circle would look differently.
Can we do something like defining the distance from x to y to be the maximum of the cosine of the angle between, okay, let me draw this. So here's point A, here's point B. Maybe I should have drawn it. And then here is the x distance and here is the y distance. So sorry. That's a very random shot. I'm sorry if it's in a completely wrong direction. It's just what I thought when I thinking about this.
Well, that is actually quite smart. I like it. So then basically, if you're trying to find maximum from cosine alpha and sine alpha, for alpha, which is between 0 and 45, that would be cosine, right? So,
Oh, but then we have the points where one of them is point.
well, but then I like your approach because it gives us some ideas. The only thing you have to be careful with is that cosine alpha and sine alpha, like together, they're their Euclidean distance is 1. But here, when you take a maximum out of them, you get, for example, that even if cosine alpha is bigger, it will just be equal to say 0.5, and then you have to scale it to 1. So you're first finding the which of two of them is bigger, and then you have to still scale it, which is a little bit not convenient because you would have to scale it all the time. But I still like the thought. I mean, I guess if you spend 5 more minutes, you'll get to the answer. Maybe we can try just playing around with it. Say, if my point y is here, then they have no distance on the y coordinate. They only have distance on x coordinate. So of course it's a maximum. So we just put 1 here. And then if we put y here, this is still much bigger than this, right? Right?
Mhm.
Okay. And so that means that we're still counting this as our distance. So the different distance between this and this is still 1. Even though, well, it doesn't look like 1 exactly. And so we can do that for a very long time here until this length reaches this length. So 1. So don't look at this point. Don't ask me what happens there yet. But say if that's 0.9 and this is 1, this is still bigger. So we'll still take it as a distance. So distance between here is still 1. So that starts looking like an answer. And then we can do the same, but in this direction. So 1 down, right? Can anybody try to work with that and show me the complete example? And while you're thinking, I'll pour myself some tea.
I think maybe on the left side we can have same thing.
Oh, that's a great idea. That's because
this.
everything is similar, right? Sure. 1 here, 1 here. Okay, that already looks like something. What do we have in the above?
We can try. Suppose we have a point here, and yeah, this one would be the max, and this is the distance between. This is the metric between these 2 points. So I think this also in the circle, right? On this
That sounds
direction.
awesome.
Yeah, and from there to here, in the vertical line of this x, this point, we can always do this, and we can do just the symmetric work and have very on top and the bottom.
Okay, then what we have is we get a square. That's why it's called square metric.
Yeah, I'm not sure whether it's correct.
Oh no, I think what you said is definitely right. If you notice, let me erase everything because it's becoming messy, right? Because if you notice, if you have point X, then we're always measuring distances like in the maximum. If we have a square which has 2, 2, 2, 2, but it's also 1, 1, then no matter what point you take, because it's on the square, one of them would always be bigger than the other. And so the distance is always 1, right? I actually wanted to ask Professor Shu what happens on this 4 vertices, because there the distance is supposed to be the similar, but then I guess if it's similar, then maximum is just any of them, which is still 1, right? So I think it should be the same.
Yeah, it's just like, well, what does it look like? It's just like what? Well, you can, the vertex is no difference from this edge or these lines, right? The side of this square. So which means if you want to take the, for instance, if you want to take the open ball on this row metric, then it will be the open square, right? Otherwise, it will be the closed square, and the vertex is just the vertex, right? The maximum is still 1. The maximum of 1 and 1 is 1, right? Just as you said.
Okay, sure. Then that means that we finally learned what a circle looks like, and now we know how to work with those spaces, right? And we can actually even try to just try to show that it's actually a metric, right? Because we still have to prove that. And so yeah, let's try to do that. So we know that I'll write the definition again so you don't forget it. Maximum of x1 minus y1, x2 minus y2, blah, 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 blah. Right? So that's how we define it. We have to prove 3 properties of a metric. Can somebody help me with the first one? Oh, does anybody remember the first one?
Because they all absolute values, so they all larger or equal to 0, and
Sure.
also we do not consider the others. They're just the same. Equality holds.
So basically,
yes.
Sure. Thank you. So basically, what the concept said is this is the first property of a metric, and also dx equals to 0 if and only if x is equals to y, right? And so what the concept said is because they're all absolute values, no matter what would be the maximum, it still would be an absolute value. So it still would not be less than 0. So this always holds. And then when the maximum of all absolute values is 0, it means that all of those absolute values are equal to 0, right? Because if at least one of them is not 0, it means that the maximum will be bigger than 0. So that means that in all possible coordinates, x and y have the same coordinate in all possible dimensions, which means that x and y are equal to each other, right? Understandable?
Yes.
Great. Then second property is, can anybody remember, remind me of second property?
The distance between x and y would equal to d of x and y would equal d of y and x.
Yay, thank you, Theodora. So basically, that it doesn't have any directions, right? And why is that true here?
We take the absolute values, so the order doesn't matter, the order in which we take them.
Sure, great. So that's also true. And then the third property, the most fun one. Is it? Oh, I'm sorry, Josh. I didn't saw that that you were writing in the chat because it's hard for me to see the chat while I'm writing the word. Oh, are you asking because why dx x is equal to 0? Oh yeah, sure. Let me show again. So basically, when we have that, we have to show 2 sides. So first, if we know that dyx is equal to 0, we have to understand from that y is equal to x. Why is that true? Because we take maximum of absolute values, right? And we know by properties of absolute values that they are non-negative. So they are always 0 or some positive number. If at least one of them, say this would be equal to 5, then maximum would totally be more than 5 or 5, right? Because, yeah. And so it means that this would not be equal to 0. So that means that all of them should be equal to 0, right? Does that make sense? I hope it does. And so it means that for all of the absolute values, they would be equal to 0, which means that x1 equals to y1, x2 equals to y2, x3 equals to y3, blah, 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 blah. And when for some 2 points, all of their coordinates are the same, it just means that x is equal to y. So we proved that first side. But then the second side is much easier because when you have y equals to x, what happens is you're taking max of x1 minus y1, x2 minus y2. But since they are equal, all of their coordinates are equal, so that would look like max of 0, 0, 0, 0, 0, which is 0. So the distance is 0. Does that make sense? Yay, great. And so now we're doing the third property. Let me check the chat. Oh yeah, great. So the third property is a triangle inequality, which looks like dxy plus dyz because in dxz. Okay. So why is that true? That's actually a pretty tricky one, so I'll give you like a couple of minutes to think about it because like that's not very obvious. Get myself my tea. So how about we try to do it for any random I? Say we know because of the absolute values that x, y, y plus Okay, does everybody know that fact? Because I think people do it in school, or I think in high school, but just to make sure. Great. If you don't know that fact, it's because the path from A to B is always shorter if you take it straight, not from something else. So that's it. And I can of course show it to you after the presentation anyway. But we know that fact, and it holds for any I, from 1 to n, which is great. And so let's notice that this thing would always be less or equal to to max of x1 minus y1. Sorry, let me erase it. x1 minus y1, x2 minus y2, blah, 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 blah. Does everybody understand why? Okay, one understand? Theodora, Chikan, Holly. Where is Holly? I'm not, I can't see everybody on the.
It seems that we lost Holly again. Well, I guess her internet connection is really bad.
Yeah, okay. Well, I will upload the lecture anyway to the YouTube so she can watch it from there. Okay, I think a lot of people told me they're fine with it. So it's just because this would always be contained in here. And so we're taking max, so of course it's always bigger or equal to one of those things. So from that, because this is just can be written more shortly as p xy. Oh, I'm sorry, I should have written p here, which doesn't matter, but okay. So this is less or equal than p xy. Then can somebody tell me what would be an upper bound for this part?
It's P of Y and Z.
Right, and for completely same reasons. Okay.
And then
So,
sorry.
no, what did you say?
I was just gonna say that for X and Z, it's going to be the same. The upper bound is P of X and Z, and then the big is the first row, which is the P.
Sure, thank you. And so, yes, we get a very nice fact, which basically looks like, to erase that, we get that this is less or equal to some of these things, right? And so, because we get that this thing is less or equal to this thing, which is this thing also, which is what we want on the left side. And now let's recall that when we were treating I, we never chose what I would be, right? So it works for any I. And so we know that for one of the I's, like they would be equal to maximum. Let me show it more better. Yeah. So what we know is we know p xy plus p yz bigger than xi minus zy for any I from 1 to n, right? And so, of course, we know that from x1 minus z1, x2 minus z2, like say a maximum from all the thing would be equal to some xm minus zm for some m. But this m, we can always make this our I equal to this m. So we can always make this like be equal to that maximum, which means that we can always make this be equal to px minus z. Does it make sense? Because I can repeat. Okay, it makes sense to Zikan and to Josh. Teodoro, any questions? Great. So we proved the triangle inequality part, which basically shows that our square metric is indeed a metric and we can use it as a metric. Okay, that's great. And then let's do that lemma, which is called lemma 20.2 in our textbook. Let D and D be two metrics on the set two metrics on X. Okay, then this and this would be their topologies they induce. And just remember that topologies they induce have bases of those both, which basically means that you take a lot of balls of size epsilon and then you construct the topology based on that. Given the basis element B D X epsilon, X epsilon, for the topology, there should be by lemma 13.3 a basis element B short for the topology apostrophe. Oh wait, I'm sorry. Reading it from a different page of my notes. Forget my stupidity, please. Also, I think I gave you a little bit of spoilers to the proof. Well, yeah. Okay. Then this is finer than this topology if and only if for each x in the big X, so basically for any element of this set X, and each epsilon bigger than 0, there exists some delta bigger than 0 such that, oh my gosh, where do I put it? Okay, such that ball in D1 X epsilon is inside ball induced by D X epsilon. Sorry. So basically, what this ugly theorem is telling us is if one topology is finer, and finer intuitively means that its basis elements are smaller than the basis elements of like a not so fine set, then we can always find a ball based on the metric which is finer inside of the ball of the metric which is not finer, right? Does it make sense? Because, yeah, I hope it does. Okay. Any questions about the lemma? Well, okay, just to remind you, what finer means is you can think about it as like, okay, just to draw, say you have some topology, and that's not specifically topology, but say this topology is made of these block elements, right? Which are basis elements. And of course, they don't look like that because that's not how properties work, but just so I give you an example. And then if you would be able to find a topology on the same set, but so that basis elements are kind of like smaller and inside, it means that this topology is much finer because the basis elements are smaller and included in those big basis elements, right? Does that make sense? Great, it makes sense to Josh and to Zikan. I hope, Theodora?
Yep, me too.
Okay, great. And so basically what happens is, let's go to the proof. I would not like torture you asking to prove it because you don't have that much time to think about it. But basically what we remember is topology apostrophe is finer than topology without apostrophe when there is a thing, when the basis element be the x epsilon, which is the basis element of this topology, contains a basis element b apostrophe of this finer topology, right? That's just something we know from the previous chapters. So that, but also we have to remember that x should be inside of this, and this is inside of this. So basically the way it looks is we have some point x, there is this ball which is the basis element of the big topology, and then that we are always able for any x find some basis element which is inside but also around x, right? And now what we have to do is to basically show that we can always within this basis element we can always find some ball with metric t apostrophe x omega inside of this, so even smaller ball which just behaves according to our rules of how we define the metric, right? And so why do we need it? Because the fact that a topology is finer just gives you an existence of some random basis element around x from finer topology. But what we want is we want to prove that when topology is finer, one ball is always inside of another. And this is not always a ball. This is just something that we know exists. And so we want it to be better. And so we are defining even stricter basis inside of it. And how do we do it? Well, yeah. Basically, we just take this epsilon small enough so it will be contained within that basis element, right? And we can always do it because we can make like epsilon infinitesimally small, okay? And it still would be a basis element. So that's the idea of a proof. Does that make sense? Okay, it makes sense to some people. That's good. The apostrophe. That's this one. Inequality. Okay, I don't see questions in the chat. So, and I know the proof is a little bit hard, especially say for example to Josh, because Josh didn't know what topology is because he just joined. So it's fine. I just wanted to give an intuitive feel of what's happening. And then basically what happens for the another side of the proof is we just do the same thing. We say if we always find a smaller ball inside of a bigger ball, which is the basis element, then basically we just apply that lemmas from the previous chapters, which tell us that if you always find a smaller basis element inside of a bigger basis element, then one topology is finer than the other. So it's just basically a very direct application of lemma called lemma 13.3. And you can always go to it after that part or watch our previous videos. But yeah, that's how it goes. And so we're gonna, oh, what happened to my computer? Okay, theorem 20.3. Sorry. So we're gonna now have a theorem 20.3, which is an interesting one. And what it says is the topologies on Rn induced by the Euclidean metric D. So D is Euclidean metric, and the square metric P. P is square metric, so the one that we were playing with before, are the same as the product topology on R. Same as the product topology on Rn. Okay, and so basically, who was given the presentation on product topology? I think it was it Theodora? Or it was?
Yeah, I did.
Can you quickly remind us what a product topology is?
So it's the topology which has as a basis all sets of a form U cross V, where U is an open subset of X and V is an open subset of Y, where X and Y are topological spaces.
Okay, that's okay. Then using what Theodora said, we're gonna try now to show why that theorem holds. And I guess we'll need Theodora's help a couple more times for various definitions, but so the proof goes like this. So say you have 2 points, X and Y, and they are vectors because those are points in n-dimensional spaces. And basically what you can do is you can check that P xy is less than equal than D xy less than equal than N P xy, which I know looks a little bit complicated, but actually isn't that much complicated. Okay, why is that so true? Well, if you think about that, how do I show that intuitively? Well, this is equal to the square root x1 minus y1 square plus blah 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 xn minus yn square, bigger than maximum of those sets I minus yi. Okay, and so why is that true? Well, if you would, for example, take that to square and then yeah, if you would, for example, take that to square, no, I think I will not be able to show that really simply. I am quite sure I can like write it down and then send it as a photo in the chat, which I don't promise would be too simple, but I would try to write it in the chat in like more or less understandable way. But I don't think I will be able to explain it very simply right now. I think it is a lot about just usual inequality theorems, which not a lot of students know because we don't have stuff about proof classes and stuff, but well, I'll try to explain my best in the WeChat groups. But yeah, let's just take it as a fact for now. And so what happens is that because a distance in one metric is always like, so this is always like this, it means that this metric would always give us less distances than this one, which means that BD is X in the BP. So what happens is that because one metric always gives like bigger values than the other, when we're trying to draw the same ball with the same radius about the same point, because one metric always gives bigger values and the other smaller values, then all the points with the same radius would always stay inside of the points with the same radius but measured with a different metric. So I hope that this makes sense just intuitively. Does it? Okay, great. And so what happens is we actually can do quite the same thing with the statement, because we know that d xy is less than or equal to square root n p xy. They are always differ only by square root n. And so what happens is we can just do this. We take a ball with metric p, x, and then we just take epsilon and we divide it by square root n. It will be contained in the b, t, x, epsilon. And that's also simple because we know that they are always different only by square root of n, which is just some constant. And so we just divide our radius by some constant to see that they always would be in the different, like in the different balls containing each other. I'll give you a couple more seconds to think about it and let me know once if you get it. Yeah. Xy is t xy, which yeah, how about I make that this b and then make xy right. Okay, sure. How about, so basically we have x and y and what we do is we have this, we have just some distance between them and then we scale it. So what happens is we just scale everything in here by square root of n, and we got a larger distance. But then even when we scale it, what happens is it's just right enough big to be bigger than a usual not scale distance, but just measured in d. And so if we want to compare them, it's nicer to change to scale one of the distances by square root of n so we can actually compare them with each other. Does that make more sense? Okay, sure. And well, you have to sit a little bit with that concept and think about it because it doesn't come that quickly, but it still looks more or less intuitive. So, and if what we recall is that we got two results. First is that BP x epsilon is in the BD x epsilon. So we got that one basis element about x with epsilon divided by square root n is always inside of that base element, but for another metric, right? So we kind of got that p metric is more finer, right? But then a second result that we got was that, erase this part, was that BD, I think, x epsilon is inside of the BP x epsilon, right? That was the first one we got, which means completely opposite, which means that BD is always the finer one. And when your first result is that one topology is finer than the other, and second result is that another topology is finer than the other, your conclusion is that they are equal. Does that make sense?
Yep.
Okay, great. So what we got is that the actually like the same topologies. And then what we have to understand is that if they are the same topologies, we just have to show that at least one of them is equal to the product topology, which I'll do right now. And then let's just take metric, sorry, it's too noisy outside. Take metric B and try to show that it's equal to the product topology. What happens is we have B, which is A1, B1, da, 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 AN, BN. And basically, how can you visualize that? It's just kind of like a n-dimensional cube, right? So you take A1, B1, you take A2, B2, and so you take their cross product, so that's a square. If I add a third dimension there, and you add A3, B3, what you get is, well, that's not a cube, that's, how do you call that thing? Well, a box looking like thing. And then you just do it for more and more dimensions, but it would mostly look like n-dimensional box. Okay, so this is just an n-dimensional box. And so our product topology is basically a topology which is made of boxes. If that makes sense. Okay, and we worked more with it like in previous chapters, but that's an intuitive idea of it. It's just a product topology which is made a lot of boxes together, and what you have to have is that they all initially cover the set you're working with, but then they also each element is included at least one of the boxes, right? So okay, so what happens is we want to show that we can always find epsilon I such that xy minus epsilon I, xy plus epsilon I is inside of AI BI. And so yeah, so that's basically what happens, right? Why? Because as I said before, our basis of a topology has to have a following property for any x. Say you have an x, there always should be a box in which x lies, right? And so now what we just want to do is we want to find a ball which contains x but lies inside of a box, which would mean that basis elements of metric P, which are those balls we defined before, are just lying inside of basis elements of product topology, which means that P would be finer than product topology. Does that make sense? Okay, and the way we do it is we're just showing that. Yeah, let me just, I think we just have to have nicer pictures that would make everything more the same. We have any random element x. We know that there is always some kind of a box around it. Okay, and it's A1, B1 and stuff, right? First, we want to find epsilon 1, which is so that this thing, x1 minus epsilon 1 and x1 plus epsilon 1, still stays inside of that wide of a box, like of the width of a box, right? And then we do the same But we do the same for the lengths. We find some epsilon 2, which is small enough so that it stays in this within the length of the box, right? And then we do the same, but with the height of the box, here and here. And then we take the smallest of epsilon 1, epsilon 2, and epsilon 3, and we got our universal minimum epsilon. Say, I think in this picture, epsilon 3 would be the smallest. So we just take everything to be epsilon 3. We take a ball around X, and voila, you have your ball inside of a box. I saw Josh clapping. That's so cute. Okay, so basically that's how we show that our product topology is finite. That our P topology induced by P metric is finer than our product topology. But we wanted to show, and originally by our theorem, that these are actually equal. What are we doing to do that? We just have to show now that product topology is finer than our topology induced by P, right? But this is actually much more easier. Why? Because the way it happens is B, P, X epsilon is actually equals to X1 minus epsilon, X2 minus epsilon, plus epsilon, X2 minus epsilon, X2 plus epsilon. So, like, in a sense, our dimensions already help us to divide our P metric into different coordinates, right? And so it already looks like a product topology. And so, yeah. Okay, and so that basically means that our P metric could already be counted as product topology. So of course product topology is finer than P metric. So they are actually equal in the end. That makes sense. Okay, great. So, oh yeah, that would be kind of a very cool part. Okay, let's consider an infinite Cartesian product, which basically means you have an infinite amount of dimensions. So we would want to try to see how those metrics work when we have infinite dimensions, right? Because that would like kind of interesting. And so if you remember how we defined the D, like Euclidean metric, I'm sorry, I don't remember how to write it properly, but it was something like square root of x1 minus y1 square plus blah, 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 right? But then, when we have infinite amount of dimensions, the sum is an infinite sum. And so we all understand that if the distance between those 2 points is quite big in a lot of coordinates, what happens is that this thing would just be equal to infinity. And we kind of don't want that. So we want that sum to converge, right? Okay. What we can do is to only look at the point when this sum converges and to only work with that. Okay, and then we can try to generalize how that would look for P. And for P, it would, for example, look like, initially it looked like maximum, right? But then we all know when it comes to infinite amount of something, there is not always a maximum, right? Say if you got something like 1, 2, 3, 4, 5, 6, blah, 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 there is no maximum there. yeah, and so basically you can, for example, try to do like something like supremum. Supremum does help with some cases. With which cases it helps? Let me. Oh yeah, yeah. A great case to show how supremum works. So say you have 1, and then you have 1 plus 1/2, and then you have 1 plus 1/4, and to infinity, right? So it will always look like 1 plus like this. And so why is it a good example? Because there would be no max, right? Because it would always go little bit by little bit further, meaning that, yeah, there is no max because it's infinite, but there would be a supremum. Oh, wait. Sorry, let me like, I made a stupid example. 1, 1 plus 1/2, 1 plus 1/2 plus 1/4, and etc. 1 plus sum of 1 divided by 2n. Right, yeah. So this would be an increasing sequence, which would grow really slowly at the end, but it still would grow. So maximum doesn't work, but supremum works, and supremum would give us an answer that supremum of the sequence is just 2, right? If you're not sure what supremum is, it's kind of like a limit, like a maximum limit. Yeah, you have to look for a more precise definition in the analysis textbook or something, or Wikipedia, but that's good enough for now. And so we can try doing that, but it doesn't always make sense because, say, supremum for 1, 2, blah 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 till infinity, it just doesn't work, right? So again, we still don't know how to handle that. And any ideas how we can try to create metric which we can work with in infinite dimensions and they don't give us too much pain? And you have the answer because we did it before. That would be a hint. Guys, we did it before. We did it. I'll hint that we did it right in the beginning of this presentation. And there was a word bar involved. guys. Remember we did that? How did we do? Oh yeah, yeah. When we had metric D, which was defined as this, what we did is we also did D bar, which was minimum of x minus y, and oh, that was norm, I'm sorry, and 1. So that's a nice idea, because basically it tells us if their distance is less than 1, keep whatever the distance was. If the distance is bigger than 1, let's make it 1. So 1 would always be maximum of our distances, right? And if you don't like 1, let's do it 100. Like, I don't care. But how can we employ the similar concept, but say to the pxy, which is max blah 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 blah. Okay, let's not do max, let's do supremum. That would be here for you. Oops. Supremum of that set xi minus yi. How can we use the same, but for this p? We just need to define p bar. Also, just to give you a sign of relief, we usually have breaks at like 6:30. 6:30 my time. That's 8:30 China time. So that means in 7 minutes. So if you'll come up with an idea real quick, we can have more break. Well, okay. Say we defined a metric d bar, which is one-dimensional metric. X, y would be x minus y, right? And so what we can do is we can define p bar between x and y as a supremum. Oh, sorry. So d bar would be a minimum between 1 and distance of x and y in one dimension. And so what we do is we take supremum of d bar xi. So to give you a better idea of how that happens, let's look at some example. For example, say you have a vector 1, 2, 3, which is x, and you have a vector 1, 2.5, 4 as y. Then we define p as a supremum of d bar 1, 1, d bar 2, 2, 5, d bar 3, 4, right? If at some point you get the idea, feel free to shout it out. So, and if you look at that, d bar 1, 1 should be a minimum between 1 and 1 minus 1, which is 0. Of course, it would be 0. That's 0. This one is d bar 2, 2.5. So d bar 2, 2.5. That's a minimum between 1 and 2 and 5 minus 2, which is 0.5, of course. So this is equals to 0.5. And then what we do is we do d3, 4, which is a minimum between 1 and 4 minus 3, which is just 1, right? Which is 1. So we take a supremum between 0, 0.5, and 1. And supremum, when we have finitely many things, is just basically maximum. So that would be equal to 1. So as you can see, we define our metric so it would still preserve what we know about disciplinary points, because 1 here is a symbol of a long distance. So basically, if it's 1, you just know that these 2 points are very far from each other. If it's less than 1, then you still have the same distance than it was before. Like, nothing got changed. So does that make sense? Okay, I got 1 thumbs up. Yeah. Okay, I got 2. That's good. And so basically, okay, so basically this P bar is just called uniform metric. That's just the name. And so the topology is used called uniform topology. I'm not sure why it's called uniform though, but well, I guess you need some name for very frequent metrics you're using. And then, yeah, and I promised a break. So how about we go to a break now? And then we return in like 15 minutes. Okay, great. I'm kind of like still staying here, like in the same room. So if you just want to talk about stuff.
I'll probably use my break to go for lunch.
Oh, what time is it now for you?
It's 3:30 p.m.
Oh, nice. So you just had the day started. Bon appetit then.
Thank you. See you in a bit.
See you. Hey, anybody here yet? How are you doing, Zakon? By the way, what tones are in your name? Cause like I think I pronounce it wrong all the time.
I think you are right.
Oh really? So what tones are those?
Um, Z is the third one. Con is the first.
Ah, okay. And what does it mean?
It's very simple. I think it's just hope like sound is healthy.
Oh, okay. But I don't know. I kind of like Chinese names. They're like so fancy. Like every time I
Yes.
ask somebody, like, "What does your name mean?" There's like a whole story behind it.
Yes. So it's unique, I think.
Yeah, it's cool. Like I don't know. I think Tedora would like agree in like say post-Star countries. Like everybody is named Artom or Daniel or Pecha. It's like you'll see so many people with like the same name. And like their parents just didn't care, like whatever it is. So yeah, you got really weird times when like there's like a high probability of having like say people with the same name, like three people with the same name in class. And there is also a very high probability that they would have the same surnames. So it's hilarious. Yep. What are you up to? Like, what are you doing during the summer?
um, um, Doing some research, but yeah, but I'm stuck in some sense.
Oh, what
And
research?
for data, some satellite retrieval data, how to deal with it.
Mm.
Hello.
Hey,
Hello.
we are sorry.
I think I just lost our signal.
Oh,
Yes.
too bad. I hope she gets back soon.
Hey, sorry,
Finally,
I don't know what, yeah, I don't know what happened to my internet connection. It was just boom and it disappeared. Uh, it, I'm not lagging right now, right?
yeah, I think it's smooth now.
Okay,
Yeah.
sorry for that. um, okay, is Theodora here?
Yeah, I'm here.
Hey, okay, great. Then let me start in a second. Dun, dun. Huh. Typically, stuff. Oh yeah, so we're talking about uniform metric. Um, dun, dun. Uh-huh. So now when we know that product topology and uniform metric topology and also the Euclidean topology are all the same, we can have the following theorem. So theorem 20.4. The uniform topology on Rj. So J here means that it can possibly be an infinite set and it doesn't have to be countable as far as I understand. Is okay, is finer than the product topology and coarser than the box topology. Okay, and they are different when J is infinite. So you would ask like, we just proved that product topology is the same as the uniform topology. Why are we trying to prove it's finer? Well, yeah, they can be equal to each other. So that like when we say finer, it's kind of like equal or bigger. So it's still there is still a case when they're just equal to each other. But we're saying finer here because what we did before, we proved that they are equal as when we assume that we're doing it for some Rn. Like we explicitly knew our n. But then in this case, this can be some infinite j, which we don't have much knowledge to work with. And we also define it a little bit different for infinite dimensional spaces, right? And so it means that in this case, when it's infinite, they actually can be like quite distinct from each other. Okay, so then how do we do that? Okay, so the proof. What we do is we would suppose that we have some point x, and then a product topology basis element u alpha around x, right? So yeah, this is product. Okay, and then so let a alpha 1 blah blah alpha n be indices for which u alpha is not equal to r. Okay. Then for each I, what we have is we choose epsilon I bigger than 0, and so that basically the epsilon I centered ball at x alpha I in the d bar metric is contained in the u alpha. Okay, alpha I, sorry. Okay, why is that true? Well, let us see. So basically, we can always make epsilon so small that it fits in that U alpha I, and we also know that U alpha I is an open set, so we can always do that. Okay, so what we have is we do our usual tool, we take minimum. So we take minimum of all of those epsilon 1, epsilon n. Well, there's no n, sorry, it can be n. Right? And so what happens? Oh no, wait. Oh, sorry, no. We do epsilon n. Why? Because we decided that for this specific from 1 to n, those are the indices at which this U alpha is not equal to R, right? So yeah, there is actually a finite number of them, and that means that we can take a minimum. Great. So we find that epsilon, which is equals to minimum of those, which basically means that we are always able to find an epsilon ball centered inside of that product topology basis. Great. What do we have after that? Okay, that P metric is contained in this. Okay, well, E-centered ball induced by P metric is contained in this basis element. Okay, and so say, for example, if we have that P xz, where z is just some random point, is less than epsilon, then what happens is T bar x alpha z alpha is less than epsilon, right? Is that understandable? Okay. Then basically what happens is that it means that z is in our base, right? Because basically if some, like say U100 is just equals to R, then of course z is inside, like it's one of its coordinates is inside. And for all others which are not complete R's, we know that we can always find some epsilon, and we can always look at z's which are inside of this set, right, as we defined it. So it would be inside of an epsilon centered ball, right? Okay, so basically we get that z would also be in this basis, and then yeah, what that means is that we just proved that like all the set which is an epsilon centered ball is inside of this, right? Because if we like our epsilon centered ball, this is a set of all points which are distance or smaller of epsilon, and we show that for any z such that this holds, z would always be inside of the basis topology, right? So we show that the ball is inside of that, is inside of this basis of this product topology. Sorry. Okay. And so basically what happens is the same happens in the opposite direction. When we have B to be an E epsilon ball centered at X with B bar metric, then basically the box neighborhood U buttons minus 2 alpha plus 1/2 would be contained in B, right? And I hope that's understandable. Why is that? Because we know that everything that's on the distance of epsilon from X would be inside of that ball, right? But then if we take 1/2 of epsilon, of course it would be inside of that ball. And so if we just make it like this, of course it would be inside of our basis element. Okay. Sorry. And so what happens is that we just get that. Okay, and so basically what happens is we just showed that we know how to make them, how to show that something is finer, something is coarser, right? Which is we just did, because we basically showed how a ball lies inside of the product topology, right? And yeah, and we just showed how something lies in the neighborhood, which is oh my gosh. Okay, we showed how ball lies inside of a box topology, but we also showed how product topology lies inside of the ball. This is why product topology is finer than the ball, and then the P matrix topology is finer than the box topology. Okay, that's what we showed. And we'll have to leave the fact that when J is infinite, they are different to exercises, which we probably would do on the day when we do a lot of exercises. We'll have to actually, when we finish the second chapter, we'll just have to find a day when we're just gonna run over exercises from different parts of the chapter, so we make sure that we can solve them. So that would be for that day.
That would be a good idea.
Yay. Yeah, actually, when do we finish that chapter? That's such a long chapter. Tikan, do you know when we finish the chapter? Is your part the last part?
I think after tutorial, we finish this chapter.
Okay, sure. And so basically, yeah, just someday we'll have to come together and well, I was thinking, should we set up a Discord server? Cause that would be interesting if we can make like a Discord server for a math club where we can write stuff. If that would be of a demand, but yeah, we'll talk about it a little bit later. Okay. And so basically, in the case when J is infinite, we didn't determine whether Rj, whether Rj is metrizable in box or product topology. And basically, the only case it turned out when Rg is metrizable is when G is countable and it's a product topology. So only case when metrizable is G countable. So G can be infinite, it just has to be countable plus product topology. Okay. And now we'll come to the theorem 20.5. We actually have just a little bit left. I think we would even finish earlier than in an hour. Okay, so the theorem 20.5 tell us that let d bar AB equals to minimum of A minus B and 1. So yeah, as always. And so that would be standard bounded metric on R. If X and Y are 2 points on RW, so those are vectors, don't forget, define D XY equals to subprimum D XY I I divide by I. Okay, so this already looks kind of interesting because we are now divided by something which is continuously growing. Okay, and so basically we want to show that D is a metric that induces a product topology on RW. So how do we do that? Well, that's a good question. First, we have to show it's a metric, right? So let's just try to show together it's actually a metric. Why does the first property hold? Well, the first property is that it's not negative, right? Hey guys, any thoughts, ideas? Then you pay right. Let me mute myself for a second. I need to check something. Okay. Any ideas? So let's look at the definition, right? So we know that D is something we have worked with for entire thing. We know that D is defined to be minimum between an absolute value and 1. So it's never a 0 or never a negative number, right? And when we divide this by I, which is also non-negative number, we get some non-negative number here. And then we take a supremum. Supremum is kind of like a maximum limit, right? So it's also would never be a negative number. So we know that dxy is bigger or less than 0. So let's show that when it's equals to 0, then xy equal to each other, right? Well, see, if this equals to 0, it means that the supremum was equal to 0. We take a supremum of non-negative numbers, which means that they all have to be 0 in order for the supremum to be 0, right? That's the same as maximum. If the maximum is 0, and you know that it's a maximum of non-negative numbers, they all have to be 0. So for all i's, this thing is equal to 0. So we don't care about that I anymore in the denominator. And then what happens is that we know that for every I, the d bar xi yi is equals to 0, which again means that a minus xy minus yi is just equals to 0, right? Is that understandable? Hello? Am I lagging? Maybe I'm lagging and I was not. Hey,
I think it's fine for you.
Okay, that's good.
Tedora, are you going to say?
Say something.
I was just gonna say I heard, and I heard what you said, and it's good. I think I understand.
Okay, sure, that's good. Second. Okay, great. So if we understand this first property, let's go to the second property. Second property was that oh yeah, that dxy is equals to dyx, right? So how do we show it? Well, let's recall again what our definition is so we don't forget it. Supremum of d bar x I y I divided by I. Okay, so why does it not care about the arrangement of x and y's? Well, you have to remember that this d bar is a metric. And so we know that second property holds for d bar, right? Hey guys. I don't know, sometimes I'm thinking like 3 hours kill people. Maybe we should do like hour and a half in the beginning of the week and then hour and a half in the second half of the week. So it's get like
Yeah, I think that that definitely works for me. It only depends on well whether you guys want to do that or not, because it's always up to the speaker, right? If a speaker wants to do that longer, then well we should do that longer. If you guys don't want to do that, we can also do that in one half hour. Yeah, I think maybe that'll be better. Well, I
yeah,
don't know.
because I feel like I don't know, like right now I'm really even tired to talk. I don't know how professors do that for like a couple of hours.
Yeah, but anyway, I think whatever you guys want. Yeah.
Okay, then I'll write in a WeChat group after that about the idea. Maybe people would like it. Chedora was going to say something.
I also think that that's a nice idea because also when you speak, it really feels tiring to speak for 3 hours, and for the people who listen, it sometimes it's hard to concentrate on it for 3 hours. And also, if we have 2 meetings, we can sometimes use one of the meetings to solve some problems.
Yeah, I think that would be like, and you would like, I think I forget stuff too quickly when it's like 1 week difference. Maybe if it's like more frequent, like it would be more focused. So yeah.
Starting school in a month, approximately. Okay, a month and a half. So if we can cover more stuff before we start school, it will be better.
Yeah. Because we're only like on like second chapter.
From the positive side, like the book is about 500 pages and we've covered 120 of them, so it's not that bad.
Yeah. Okay, that's good. So yeah, let's continue on like why is the second property true?
Doesn't it follow directly from the fact that D bar is symmetric?
Yeah, that's just how it is. Because if that holds, I mean that this would just be equal to supremum dy, sorry, yi xy, and this in its own turn is dy x. So we just write two more equalities and we're done. That's why second property holds. And then third property is triangle inequality, right? So we have to prove that dxy plus dyz bigger than equal than dxc, right? Any ideas for that? We know this. That's helpful. What happens if we divide it by I? Nothing happens. And then the rest part of the proof is really similar to what we were doing with the previous one. Remember when we were doing, I think when we were doing the B bar, when we're trying to prove it symmetric, we did the same trick.
So can we use that this part would always be smaller than the supremums? I'm sorry, like this part is always smaller than the supremums of this and this, and this part is always smaller than the supremum, blah blah blah, supremum of.
But if it's slower, it's not really good to say it's slower than supremum because it breaks your inequality. But we can do something else. We know it works for any I.
Okay. Wait.
But yeah, I like your idea that we can just write that this is smaller than the supremums of that. Oh yeah, just go for it. Erase my stuff. I like how you write Z. It's like it is how I was taught to write it in like primary school in English classes. Then I came to DK and people told me that's not how you write it.
I think primary school I understood with me for too long time. So.
Okay, so Theodora got us the most part of the proof. We know that the sum of those two d's is bigger than that d bar stuff divided by I for any I, right? And then I guess I don't know one cool fact about supremums. So say, if you know that some inequality holds for any of an element of a set, then it holds for the supremum. Because the supremum is kind of like the maximum limit, right? And you know that it holds for limits. Say, say for example, you have some sequence A1, blah, 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 right? And so if you have that some A is bigger than for any I, then we know that A is bigger for limit an and goes to infinity. We know that fact, right? And because supremums are kind of like maximum limits, then this would hold for supremums too. So a supremum of an. So that means that what we just proved is actually can be written as dxy plus dyz less than dxc. Okay, so we proved a triangle inequality. So that means what we did prove is that D is a metric. Great. Okay, so then we have to show that D is a product topology. Okay. So how do we do it? We say let U be an open in metric topology, and then X in the U, X is a vector. We find an open set V open, in the product topology, such that X in the U V in U. Okay. Okay, and so what we do is we are choosing an epsilon ball B D X epsilon, right, lying in the U. Okay, then choose n large enough that 1 divided by n is smaller than epsilon. So yeah, that's a very frequent analysis trick. But if you didn't saw it before, if you think about it, and epsilon is just some constant, and natural numbers are going as large as we want. So if we divide by natural numbers, of course, at some point that would be lower than some constant. Okay, and so what it means is that what we're doing is we get V, the basis element of the product topology. Okay, so we'll write it like that: x1 minus alpha, x1 plus epsilon, sorry, xn minus epsilon, xn plus epsilon by r, blah, 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 blah. And what we want to show is that V is actually in that ball, right? So how do we do it? So if we take some y in the RW, and we say d bar xi yi divided by I is less or equal than 1 divided by n, for I bigger than n, right? Why is that true? Because we know that this is defined to be a minimum between xi minus yi and 1, right? So it's maximum 1, and we divide it by I, and we take I to be bigger than n. So of course, all the thing would be less or equal to 1 divided by n, right? And so what you get is that your dxy would actually be looking something like like it is supposed to look like supremum of d bar xi yi divided by I, right? But then what we realized is that when I gets big, like this thing gets really small. So we don't care about it because it has no chance of becoming the biggest element of the set if it's going down. So we can cut it. And the way we cut it is we write it as here. We write it as maximum of the x1, y1, 1, blah, 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 dxn, yn divided by n, and 1 divided by n. And that's it, right? And so we don't, and of course this can become a little bit bigger than our dxy, that's why in upper bound. Because, for example, we may never actually get 1 divided by n, but we do count it in here. Okay, and so it means that if I is in the V, that basis element we were choosing in the beginning, it means that this dxi should be less than epsilon, right? And so it means that this V would actually be inside of that ball with a radius epsilon, right? Okay, and so what did we just do? We chose some I, and we showed that and we showed that we can always make a ball so that it would cover the V basis element that we chose before. And we did it with a couple of tricks which involve just like simple inequalities when we just play with stuff with maximums and supremums and make bounds as we want it to be, right? And so that's really not that bad, right? Okay, and now what we want to do is we want to look at some basis element U, which is some cross product I plus for the product topology, and then UI is open in R for I equals to alpha 1, alpha n, and then UI equals to R for all other indices, right? That's basically what we did before. Okay, and then what happens is we have some X in the U. And we want to find some open sets V in the metric topology such that X is in the V and V is inside of U, right? And so what we do for that is we choose an interval xi minus epsilon, xi plus epsilon, right? Oh, sorry, epsilon I, because we're doing it for every index of I. In R, centered about xi. Okay, and so basically what we want is we want those epsilon i's to be less or equal to 1. And then what happens is we do epsilon equals to minimum of the set epsilon I divided by I for all i's which are those specific coefficients for which we have that UI is not equals to R, because we don't care about others. because they would always lie inside. We just only want to make sure that the ones that which are limited, we are covering those and we're lying inside. Okay, and basically, as you can see, those you would of course have a minimum for that because there are only limited number of those, so we can take a minimum. And you can also see that as I grows, you have them going down, which is also good. And so what do we have? We have x in the BD, x epsilon in the U. Okay, I hope that this is understandable. Why? Because we just defined like BD to be a ball with radius which is super small, and we also defined that radius based off all kind of UIs and their limitations. So we were specifically making that ball small enough so that it would fit in, right? And so when we finally did that, what we want is we want to assume there is some point y in this ball, x epsilon. Then for all i's, you have t bar xi yi divided by I less or equal than d xy less than epsilon, right? Why is that? This happens because of the definition of d, right? Because d is defined to be a supremum among them, so of course it's bigger for any I, and we also know that it's less than epsilon just because we are looking in a ball with radius epsilon. So I hope that's understandable. And then what we do is if I is equal to one of those coefficients for which ui is not equal to r, then we know that epsilon is less or equal to epsilon I divided by I. Why? Because we define it to be so, because we define it to be a minimum of all of them. And so what we get is we get d bar xi y less than ai less than 1. Okay, so I think that's also understandable, right? Because because you know that g xy divided by I is less than epsilon, and epsilon is less or equals than epsilon I divided by I. So if you forget about this part, you get this part, you cancel i's, and you get the inequality you wanted, right? And we initially, before, wanted those epsilon i's to be less than 1, is just how we defined them to be. So this is all understandable for now, I guess. And so it follows that xi minus yi is less than epsilon I. Okay, and this happens for any I. And it means that y lies in that basis ui, right? Why? Because we specifically made it so that a distance between x and y, where x is just something in that basis element, would be smaller than the radius around x in any of the dimensions. So we came to a conclusion that I lies in that product topology. So basically, just to summarize what we did, is we assume that there is a point I in the ball with radius epsilon, and we prove that it would always then lie in the product topology, right? So we kind of show that the product topology lies inside of that ball, and I hope it makes sense. And if it doesn't, that's actually the end of my chapter, so we can go over any part that you feel confused about. Okay, so to remind you what we were doing with that theorem, I know it was a very long theorem and the proof is for a page, but the idea of a theorem is you want to define that metric D, like which we defined, and of course it's a little bit of a weird metric, but well, it makes sense. And we wanted to show that it induces product topology. And it's kind of hard to do it out of nowhere. So what we did is we first tried to show that that this topology which D uses is actually finer than product topology. So topology on D is let me do it like this. Then product, and we show that product topology is actually finer than this topology on D. And so that's how we came to understanding that the product topology is actually a topology induced by D. So because they are equal, right? That was like the general structure of a proof. And then to prove each of those points, what we did is we were just trying to find basis elements inside of basis elements. And the main confusing work, which we did, was just to always find good enough radiuses. Because we all intuitively understand that one basis would be inside of another if we make that radius small enough. And to make it radius, we just have to do a little bit of arithmetics and show which radius is small enough. And that's all. That's basically everything we need to do. That's the essence of proof, and we will like fine going over any part of it. How did that song go? Say something, I'm giving up on you. Dun, 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 dun.
Don't give it to us, please. Don't.
I'm just joking. I just didn't. That's like every time I want to say something, that's like the first thought that pops into my mind.
Yeah.
Was this song by Demi Lip? It was like by Christina Aguilera, right?
I don't know. That's literally like every time I present, I also think about saying say something, and then I'm like, oh no, that's the song. I should not continue.
So yeah, and listener should repeat from any part of the presentation.
I think I got most of the things. I will probably go over the last two theorems again. Or read them. Because I think I got like the steps, but overall I'll probably need to go over them.
Okay, give me a second. Oh, and I think we only have like 2 sub-chapters left, and they aren't that big. And then we also have supplementary exercises, which can we do on some other day. But yeah. Okay, so the last 2 theorems. This is 20.5, 20.4. Okay, so 20.4 basically is saying okay, that uniform topology, and to remind you, uniform topology is just that the bar, but defined for infinite dimensional spaces, right? So it has a little bit more of a complicated definition, which is, I think, supremum of d bar xi minus yi. Yeah. So that was a definition of the uniform, topology. And so, is that your sister?
Yeah, I'm sorry, I forgot to mute myself.
No, it's fine. Is she feeling better today?
That's the other sister. I have two sisters, but the other one is better too.
Okay, that's
Baby.
then basically what we know about uniform is that we want to show that it's actually finer. So let this be finer. Then a topology, then the product topology. But it's coarser, so I mean that some else is finer than the box topology. Okay, so that's what we want to show. Actually, we did show that they are equal, but we showed it for like Rn when n is finite. But there is a strong inequality when n is not finite and it's just something infinite. And yeah, okay, so that's what we want to show with that theorem. And so basically for a proof, what we did is we took a point x and some product topology basis element pu alpha, and say that alpha 1, alpha n are indices at which u alpha I is not equal to r. So we just took some random point in the product topology, right? And so basically to show that our uniform topology is finer than the product topology, what we need to do is just we have to find a basis of a uniform topology which contains x but is inside of this. So we have to find something in between these two things, right? And I guess that's not that hard, right? Why? Because what you do is you basically choose for each of those u alpha i's. So look, you have two probabilities. First is ui is just equal to entire space R, which is awesome because it means that whatever sector of it you take to be like xi minus epsilon, xi plus epsilon, it always would be in the R. So you don't have to care about it. And so we don't care about it. But then there is also a probability that ui would not be equal to R, but there are only finitely many of them. And that's great because we can always find some xi minus epsilon I, xi plus epsilon I, which would lie inside of that ui, right? Because we can just make epsilon really small, and we know that I is open. So why is it important that that UI is open? Is, well, because open sets, if you think about them, not in a topology kind of way, but in an analysis kind of way, they look like AB is an open set. This is closed, right? If UI was closed, X could be lying on that edge. So we wouldn't be able to find something between X that would be inside of UI, right? Because if A is equals to X, whenever we go into X minus, like A minus like epsilon, it's always outside of AB interval, which is bad, and we don't want that. But we're happy because UI is open, which means that whenever we take X, it's not A or B. It means we always can find something small enough to fit into AB. So we can always find something like that which lies in here. And we do it n number of times. Because n is finite, what we do, we take a minimum of all of those epsilons. And what happens? We call that just an epsilon, and we make a ball with a radius epsilon. And it's for sure it would be inside of our product topology basis. Do I need to draw that, or is that understandable?
I think I get it.
Okay, that's good. So we just showed that product topology, that uniform topology is finite in product topology. What we have to show is that box topology is finer than uniform topology. Well, how do we do that? Again, we take a basis element of uniform topology, which is some ball, B X epsilon. That would be some of our bases which contain X. To show that box topology is finer, what we do is we're trying to find something in between so that it would lie inside of this ball and would contain this X, some kind of V. And so what do we do with that V? Well, let's call it U, sorry. That would be easier because I would speak with my notes. So this is really nice because we just do U equals to X alpha minus 1/2 epsilon, X alpha plus 1/2 epsilon. And that's everything we need to do. Why is that everything we need to do? Well, because again, see, we have two probabilities. Oh no, sorry, wait, we don't have two probabilities. We're just doing this thing. We know that in any direction we have radius of epsilon around X. So if, and now we would just make a box around X, but the half of the length of the box would be, but okay, if the side of the box is epsilon and with the diameter of this ball is 2 epsilon, it means that the box fit like this. Because what happens is that we have radius epsilon, but half of the side of the box is only epsilon divided by 2. So of course it fits. Does it make sense?
Yep.
Okay, great. So we just found a box inside of a ball. How interesting. So it means that our box topology is finer than our uniform topology. Whew. Okay, was it understandable?
Uh-huh.
Okay, great. That was theorem 20.4. You're trying to find product bases. You're trying to find ball inside of product bases and then box inside of a ball. Okay. And then what happens in theorem 20.4 is we define that interesting metric dxy, which I actually kind of like it. It's a smart way of doing things. xi divided by y. And so we wanted to prove that it's symmetric and it produces the product topology on the RW. So, well, how do we do it? It's not that hard. We did 2 steps which I explained before, right? So the first things we did, oh yeah, sorry, 0 step. Prove it's actually a metric. Prove it's a metric, and I'm sure you guys can do that at this point of time. The only problem we did have is that you had to like think of that you have to divide by I and then to make a upper bound was that Theodora did, and then just know that supremum would always be smaller than A for all of its sets elements. It's less than A, so that's good. You know how to do that. I believe in you. So, and then for like last 2 parts, what did we do? Is we did a cool thing. Basically, okay. So we wanted some U, which is open in the metric topology. Metric topology meaning that topology induced by D, right? And then what we wanted is we wanted to show that product topology is finer than topology induced by D, right? So we wanted to show that if X is in U, there exists some V which contains X and inside of U, and this V would be from product topology. And this U is from D-induced topology. That makes sense so far, right? Okay, great. And that's what we're doing. We just had to do it in a little bit of an ugly way, but basically it's not that bad. So we have some BDX ball lying inside of the U. And then we choose N so that 1 divided by N is smaller than epsilon. Okay, and so basically what happens is we take that V, which is X minus epsilon, X1 plus epsilon, X2 minus epsilon, X2 plus epsilon, blah, 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 blah. Okay, where epsilon is the same radius. So this looks fine, but yeah, and you have to remember that it's only for a finite number of things. It's sorry, I'm scrolling. Okay, and so it continues till xn, and then it just multiplies by r, right? So this is a basis of product topology. Okay, and so what happens is we want to show that this basis product topology is in this ball. Then how do we do it? It's actually really simple. What you have to do is you have to assume that, okay, you have to assume that the okay, that if y is in the V, then the dxy is less than epsilon, and it means that y is in this ball, right? That's our assumption. So why does it work? If our product topology is inside of the ball, then any element which is inside of the product topology is inside of the ball too. So basically, if we show that for any element in the product topology, its radius 2x would be smaller than epsilon, we would show it lies inside of the ball. So we show that V is actually inside of B. Sorry. Does that step make sense? Because I know it's conceptually complicated, but okay, it makes sense to Theodora. Okay, And so basically, this also isn't that hard, because what we do is we realize that d bar xi yi divided by I is less than n for all I bigger than n. Why? Because this is less than 1. This is bigger than n. Then it's of course less than 1 divided by n. And so it means that our dxy is less or equal than max d1 xn y1 divided by 1 blah blah dxn yn divided by n, and then 1 divided by n. And I think I explained why, but that's basically because they keep getting lower, like those values of those d bar xi yi divided by I are smaller than 1 divided by n. They would not help us find our maximum values, so there is no use in them, we'll just cut them out. Okay, and so we found an upper bound for that. And so what happens is that we know that that if that is true, if y is inside of the v, what happens is they are all are less than epsilon. Oh yeah, sure. Sorry. So basically, if y is inside of v, then we know that each of them would still be lower than epsilon. And that also means that the maximum would be lower than epsilon. And so it means that this dxy is lower than epsilon, which means that y is also in that ball around x. So that means that this works. Is it understandable? Any part I should go over? Okay, great. I got one commentary, it's fine. Okay, great. And so basically we just showed that product topology is finer than our uniform topology because we find a product basis inside of a ball, just tweaking something with number n, right? So we just did a very common analysis trick. And though what happens later is we're just doing the same thing, but then otherwise we have some product topology basis, and we're trying to show that if it contains some x, there is some v which contains x and inside of it, and this v is some ball actually, right? Okay, and this is not hard to do. Why? Because what we essentially know is that for this thing, only finitely many parts of it are not equal to r, and all of them, others of them, are equal to r. And of course, when they're equal, like some of the dimensions are just completely equal to r, they contain everything in that dimension. So we don't have to care about that. We only have to care about the first n. And so for those first n, of course, we can always find some intervals. So if you have ui, you of course can find something like xi minus epsilon I, xi plus epsilon I. And I think I explained why before, because ui is open. And so what happens is you just do that for all the times, and then you take epsilon minimum epsilon I divided by I. And of course you would ask, like, why do we have to divide by I? Why can't we just take minimum of epsilon i's? Which is a legit question, but it has a meaning because what we're doing is we're using the metric which divides by I. So in the later part, when we would apply our metric, our i's would cancel and everything's gonna be good. So that's why we have to divide by I. So that was just a small trick, which is kind of like you know what you want to reach at the end, so that you do it beforehand, so you don't have to struggle in the end. So that's why we divide by I. We define epsilon to be like this. We take a ball with epsilon, and of course the ball would be inside of that product topology because we specifically choose A to be small enough, and it would make like the uniform topology finite in product topology, meaning they are equal. And that was the end of the chapter. And it's already 10 in China. So, yay.
Thank you very much. Yeah, it's a very good presentation. Well, one last comment on this section is, well, you learn this kind of equivalency of topology and so on. So this kind of thing, one of the, I think, most intuitive application or a very good example is, maybe you can try to Google, say, the difference on the metric space, which is you gave me two matrices, and then ask me, well, what is the difference between matrix A and matrix B? Okay, so then you may find that there are like 10 methods, or maybe 11, or maybe 12 methods, or 12 ways to define the distance for the metric on the matrix space. But then it turns out that they are all equivalent. And why they are equivalent? After you read this chapter or this session, I think you are able to understand it. I hope you can try to Google it and try to find, okay, what is the definition of the metric on the matrix space? Okay, MM. Okay. Anyway, yeah, thank you.
Oh, I actually have a question. That would be a stupid question, but anyway.
What was that?
Yeah, I was always told topology is that fun thing when you work with like holes and you make donuts into cups and stuff like that. Where is it?
Oh, that's a good point. Where is that? Yeah, where is the hole and where is so-called the genius, right? The genius of a surface and this kind of thing, right? This is what I mentioned when we discuss about the continuous function. So when you know what is the definition of a continuous map or a continuous function, you are able to study this kind of whole stuff, right? The genius stuff on the surface, because that's kind of thing, a study the invariant or this characteristic of this kind of surface under the continuous map, which is the reason why we're interested in continuous map. Okay. And then after you get a fully understand of the continuous map, you may need to understand a little bit more. If you want to study this kind of whole thing, you may need to study a little bit more on the section, I think, 22, the quotient topology, which is something tell you, okay, how can you, starting from the dimension 2 stuff, the surface, how can you make something really weird like the Klein bottle, like this kind of Mobius, Mobius band, right? This kind of thing. How can you make this kind of thing in the sense of topology? Okay, it's by the quotient. And after that, you can construct some examples by yourself, and then if you really want to do this kind of thing, which is so-called the classification of surfaces, like counting the holes on the surfaces, you will need another thing, which is so-called the algebraic topology, which is something that really about that. Okay. Although this is a really long tree, right? It's a long shot, but I think this is the best way to learn this kind of thing. Well, this algebraic topology is named after algebraic, right? Because it will need the abstract algebra. The reason is you try to do the classification, you try to count how many holes on it, by finding so-called the fundamental group. Okay, you try to associate a topological space with a group. Okay, and try to associate a surface with a group, and then as long as you can know what's the group structure of this fundamental group structure of this surface, you will know how many holes on it. Okay, and this is something very interesting. But unfortunately, I don't think in this summer we will go to that far. So maybe if you guys are interested, we can try to study some algebraic topology after we, I think maybe finish at least finish chapter 3. Okay, after we finish chapter 3, probably we are able to learn some algebraic topology if you are interested. Okay.
Oh.
But
Okay.
I would say that's a long shot. Okay.
Okay.
Otherwise, you don't know the language, how you describe the holes on this surface, right? That is a problem for you at this moment.
Or we can do a seminar on like combinatorics, because I'm still looking for some like, I don't know, more pure math courses. I don't know, like.
Yes, that would be a good idea, I think. But to be honest, I know very little about the combinatorials. I think when I was undergrad, I only take one course about combinatorials. It's very elementary. So I would suggest that find someone who are interested, and then, well, I think Italos will be a very good person to stay there and try to answer your questions. Okay, and you can still do this kind of thing. Try to do some presentation, and then I believe you can do the same thing with Italos. Yeah.
Okay. Thanks a lot.
Okay, I think I will see you guys on Friday. Is that correct?
Yeah.
And we
See
can
you
also
later, and we
discuss
should discuss.
Yeah.
And
Okay.
maybe Osman
see
would
you.
finally join us, because I think he's over with his exams or something. Yeah.
Ah, that would be good. That would be good. Okay.
Yeah. Then see you later.
Okay, see you hopefully on Friday. Yeah, and we can discuss about this. We'll cut it into half on each week. Yeah. For this 3 hours, 1/2 hour, 1/2 hour. Yeah. Okay. See you.
See you.
See you.